Welcome to this Dave on Data crash course on random forest machine learning using Python. The mighty random forest is a production quality algorithm. It's used all the time in real world machine learning and data science and analytics projects. And the best thing is that the random forest is as simple to understand how it works as it is powerful. And in this crash course, I aim to prove that to you. So what we're going to talk about today at a very high level is how the random forest works. Now, this video is going to assume that you know decision trees. And if you don't, just check out this video up here on my channel. It's a very detailed crash course on decision trees. And once you watch that, you're totally good to go for everything I'm covering here. Another thing you need to know is if you'd like to follow along, there is a link down below in the description, and you can ask me to send you the files for this particular crash course. So I will send you a PDF of all the slides. I'll send you a Jupyter notebook of all the code, and I'll send you CSVs of all the data files. Okay, and with that, let's just go ahead and jump right in and talk about why we might not want to use a single decision tree, but prefer the mighty random forest. So as much as I love decision trees, for as often as I teach them in my online and live courses, they have a very particular problem. Decision trees suffer from what is known as high variance. And we're going to think about variance from a couple different perspectives. So first up, we're going to think about variance as being akin to complexity. Now, as a data scientist, applying machine learning to your real-world situation, whether you have the title data scientist or not, you're stuck between the proverbial rock and a hard place. That is, you have to add variance or complexity to build the most useful models. But you don't want to add too much variance, as we'll see on the next slide, because if you do, then you're going to get a model that overfits. And I'll talk more about that. Now, what's super interesting is that machine learning algorithms exist on a spectrum. On one end of the spectrum, they have low variance, which is reflexively known as high bias. So high bias, low variance. And then on the other side of the spectrum, you have high variance and low bias models. So let me give you an example. A traditional machine learning technique is known as logistic regression. It comes from the world of statistics. It's useful for predicting yes, no kinds of things. It is a relatively high bias, low variance algorithm. By way of comparison, decision trees are on the opposite end of the spectrum. And this is super useful, and it can also be problematic, as we'll see in this particular crash course. So the main thing to remember is the decision trees exhibit high variance. So another way to think about this idea of high variance is not only in the idea of complexity, but also in this concept of if you change the data fed to the algorithm, the resulting model changes. So in the case of trees, you can say, hey, look, if I change the data that I provide to the tree, I'll get a different shape. So if I have data set 1, I'll get a tree that looks like this. And if I give it a different data set, it'll look like that. It'll look different. That's another example of high variance. And decision trees have high variance. So to really cement this home, check this out. So this is a sample of the data set we're going to use in this crash course. It's the same data set that I used in my decision tree video, which you can get up here if you're interested. And what we're trying to do here is use various attributes of US citizens to try and predict how much income they make. And this is data set 1. So I'm going to use this as an example of building an intuition of how trees have high variance. And then we move over here and we can see that I've actually changed the data set just a little bit. What I've done here is I've added a row ID, which is for teaching purposes only. This is a bad idea. Don't do this. I've actually done it by accident by pulling data from a database and forgetting to drop the ID column. So it is possible to do this. Bad idea. Now, what ends up happening is that we can use both of these data sets. Yes, you can train a real world decision tree from 10 rows of data and only 2 columns, 10 rows of data and only 3 columns. You can totally do that. And if you use the defaults for the decision tree classifier class in scikit-learn, you will actually get radically different trees. And let's see what that looks like. So as I said, we can use those data sets on the previous slide to train real world trees. Not a good idea, but you can totally do it. And what we can see here is that this is the tree that you get from that first data set. 10 rows of data, 2 features, you get this resulting tree. But notice if I use the same exact default settings on the decision tree classifier in scikit-learn and run it with the second data set, this is the decision tree that I get. This decision tree is 100% correct. It gets every prediction from the 10 rows of data, correct. It does it 100% correctly. And simultaneously, this model is completely useless because essentially what it says is anytime your row ID is 7 or less, I'm going to predict that you make less than 50K. And if your row ID is greater than or 8 or greater, then I'm always going to predict greater than 50K. So this model is simultaneously 100% accurate with the training data and 100% useless. So this is a problem with decision trees. So what ends up happening is that we very rarely use decision trees, single decision trees in production scenarios. We just don't. We might use them for data analysis in some situations because we can present the tree to a client or a business stakeholder and explain it to them, but that requires a relatively simple problem with a relatively simple tree. So in general, we don't usually use decision trees. One thing that we do though is make sure that we optimally tune our trees. If we use a single decision tree, we have to tune them. There's multiple hyperparameters that you can tune. I'll have a future video about doing that, by the way. And you set these knobs and dials, and then you get it to tree the best that you can for your particular data set. You absolutely have to do that. But single decision trees, once again, they're not really all that useful. So what we end up using most of the time in practice is a collection of trees. We want to take advantage of the high variance of trees, but instead of it being a downside for us, instead of us giving models that overfit, we're going to want to use the high variance of trees to build something that's even more powerful than a single decision tree could be. And one example of this is the mighty random forest. So the mighty random forest is a production grade quality machine learning algorithm, wildly useful, used all over the place, and it's based on decision trees. So all the knowledge of decision trees that you have helps you learn the random forest and makes it actually really quite simple to understand. But before we start talking about the nitty gritty of how the random forest works, we need to pop up a level and talk about the wisdom of the crowd. And I'm not going to read this for you. This is one definition of the wisdom of the crowd. Intuitively, the idea of the wisdom of the crowd is if I grab a big enough group of people and they have diverse backgrounds and diverse opinions, if I collectively use their wisdom, let's say to vote on something or to create a prediction or something like that, in general, that group of people will tend to be more accurate than any one human being, even if that human being happens to be an expert. And these are the various qualifications that are necessary to get the wisdom of the crowd. Now, in machine learning, this idea of the wisdom of the crowd is known as ensembling. And I'm not going to read you all this. This is really super technical, and here's some more technical gobbledygook, but let me just explain it to you intuitively. An ensemble is a collection of machine learning models. So in the case of the random forest, not surprisingly, based on the name, it's a collection of trees, right? Because the forest is a bunch of trees. It's a collection of individual trees. And in order for an ensemble to work, for it to exhibit the wisdom of the crowd, and in this case, for a collection of decision trees to actually work better than a single decision tree, then we need to make sure that every single decision tree inside the forest is radically different from each other. Because remember, we need to have diversity. Okay, we have to have diverse trees in our ensemble. Otherwise, we're not going to get the benefit. We might as well just use a single decision tree. Now, what's awesome is that the random forest, the algorithm, the technique is specifically designed to manufacture independence and diversity across trees. So the random forest essentially gives you the wisdom of the crowd with just a few lines of Python code. So it allows you to go from a single decision tree to many, many decision trees in an ensemble, and what you typically get are better quality predictions and more reliable predictions over time by using a random forest as opposed to a single decision tree. So we're going to explain how this works at a high level, intuitively, starting with manufacturing independence. So the mighty random forest, the algorithm, manufactures independence across many, many decision trees using three mechanisms. And the first one we've already talked about, which is the random forest takes advantage of the high variance of decision trees and says, look, I can use that. If I alter the data that I give to a tree inside the forest, it'll probably be different than the other trees. So I'm going to do that. So that's the first thing it relies on is high variance of decision trees. And the next step, it uses a technique called bagging. And I'm going to explain bagging in more detail. But the easiest way to think about it right now is bagging provides different rows, random rows, to the trees in the forest. So tree 1 will get these rows, and tree 2 will get these rows, and they might have some of the rows in common, but they'll have a lot of rows that are completely different. And because they have different rows of data, because of the high variance of decision trees, you'll have different trees, which is a good thing. Otherwise, you don't have an ensemble. And then the last technique that random forests use is they also randomize features. So if we think of bagging as randomizing the rows, randomizing the horizontal, then feature randomization are the verticals, the columns, the data features. Okay, so let's talk about bagging first up. We know that trees will radically change their shape if you give them different data. Bagging, which is short for bootstrap aggregation, takes a single training data set, takes your single set of data, and then, quote unquote, manufactures different data sets, and then provides each one of these different data sets to all the trees in the forest. Different trees have different data. They look different from each other. Boom, we get an ensemble. Now, the magic of bagging is pretty simple to understand. It relies on random sampling with replacement. And I'm going to draw some stuff here on the slide for you, really super simple. Not my best graphic design work, but it gets the point across. So let's say that I have a jar. So this is my jar right here. Okay. And in this jar, I have marbles. That's what these little circles represent. And I have a blue marble, a green marble, a red marble, and an orange or yellow marble. Okay. Now imagine that I actually can't see into the jar, even though you can see into the jar right now. I'm just showing you what the marbles are like. And because I'm a data nerd and I have no life, I'm hanging around on a Sunday afternoon, let's say, and I've got my jar of marbles, and I shake my jar of marbles up because I'm bored. And then I reach in and I pull one out. And let's say I pull out the blue marble, just at random. And I say, well, isn't that interesting? And because I'm bored and I have no life, I grab a Post-it note and I write the blue marble down, and then I drop it back into the jar. Now, I can repeat this process of shaking, drawing, and writing things down over and over again. And if I write it down on a Post-it note, maybe I get something like this. So I do 4 draws at random from my marble jar, and I get blue, orange, orange, and green. I can think of this as an analogy to my data set. Okay. So in this particular metaphor, in this analogy, these marbles represent individual rows of data, and these Post-it notes represent these manufactured data sets. So if I just do this, I can create as many lists as I would like. Okay. So I've got this one right here, and I create a new one that's red, green, orange, red, green, blue, so on and so forth, okay? Now, the thing about bagging is that these manufactured data sets, these little Post-it notes, they must have as many items on them as the original data set. So I had 4 marbles over here. I got to have 4 entries. I do 4 draws. If I had 10,000 marbles, I would do 10,000 draws, and I'd have 2,000 entries on my Post-it note. That's just the way it works, okay? Now, here's what's super important. Because we're doing random sampling with replacement, when we create these synthetic data sets, these Post-it note data sets, we can get duplicates. And in fact, that's desired. We really, really want to do that. We really want to actually manufacture the data sets to be different. And some data sets are going to have different emphasis, just random. So for example, this right here is, this data set, this Post-it note is half orange. Now notice that in the original jar data set, only 1/4 of the data is orange. So this data set, this Post-it note, is overrepresenting orange. That's okay. We want that, because what we'll be doing with a random forest is making lots and lots of trees from lots and lots of Post-it notes. So it's okay if some of the Post-it notes are overrepresenting certain parts of the data set and not others. Totally fine. No worry about that. And like I said, make sure we're crystal clear on this. In this metaphor, the rows of data in your data set are akin to the marbles. Okay. Now, bagging is awesome. And here's one of the primary reasons why bagging is awesome. Because we do random sampling with replacement, not all of the original data is in these synthetic data sets. And by the way, these synthetic data sets are known as bags. So let me go back up a slide. So this is a bag, this is a bag, this is a bag. Okay. So these are 3 bags. That's the technical term, bags. Random forest is fun, isn't it? So I've got my bags here. And notice if I look at this bag here, blue, orange, orange, green, and if I compare it to the original data set, notice that red doesn't show up, okay? And if I look at this one, this bag here, red, green, orange, green, blue doesn't show up. So because of random sampling with replacement and because of duplicates, not every row of original data is going to show up in one of these bags, okay? So that's super important. Let's imagine here that this is a subset of our data that we're going to be using in this crash course. This is bag 0, right? Our first bag. And what we can do is we can say, look, I can take all the data that's in this particular, data frame here and compare it to my original data set and say, hey, which pieces of data were not included in the bag because of random sampling with replacement? And I can create another data frame of those rows. And that is known as OOB. Yes, out of bag or OOB data. So, by the way, if you talk to machine learning people and you say OOB, they're not going to think you're crazy. They know exactly what you mean, right? Out of bag data. So here's the great thing, though. I can keep manufacturing these bags, right? So I can create bag 1, and it's going to have OOB data. And here's the thing, because bag 0 and bag 1 are extremely unlikely to have the same data. With a very large data set, the probability is basically 0 that they're going to have exactly the same data. They have different data in the bag, and they have different data out of the bag. And the random forest, as we're going to talk about later on, uses this out of the bag data to do awesome things. So bagging is super, super useful. So that's randomizing the rows, right? If I randomize the rows, tree 0, which is created from bag 0, is going to look different from tree 1 created from bag 1. So that's the rows. Moving on to feature randomization, the random forest doesn't stop, because conceptually the idea is if a little randomization is good, it's entirely possible that a lot of randomization is even better. So in the case of the random forest, that is true. So let's take an example from our data set here. So this is all of the columns of the data set. And by the way, if you opt to get the files from me, in your zip file, you'll have a test set and a training set CSV of the data. So you can see here age, work class, education num, marital status, occupation, so on and so forth. And then lastly, here's our label, the thing we're trying to learn how to predict. So technically, in machine learning, these are all of our features, and this is the label. We use our features to try and learn the patterns to correctly predict labels. That's what we're trying to do, build a model that can correctly predict income from all this other stuff. Here's the thing. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 features. The random forest says, look, if I give each tree a subset of the data, that will help to make sure that all the trees are different from each other. Because we already have the bagging, we already have different rows, but we're also going to use different features. And by default, the random forest classifier in scikit-learn, which is the class that you use for predicting labels, right, is set up to actually take the square root of the features at random. So if I have 14 features, square root of 14 is about 3.7. And if we just lop off the decimal portion, which is typically done, we say 3. So what ends up happening is that we're essentially restricting the amount of columns that are given to the trees. And since they're picked at random, that also means that every tree is going to be very, very different from every other tree, because we've randomized the rows with bagging, and now we're just randomizing the subset of columns that each tree can get. Once again, just make sure we only use the whole part. We don't do any rounding. We just lop off the decimal part and say it's 3. Let's take this idea and say we're building a new tree from scratch. So we're going to build tree 0. So we get a bag, right? We do our bagging, we get bag 0, and we say, okay, cool, we got our bag. We can use this bag to train a decision tree. And then the first thing the random forest algorithm says is, okay, tree 0, you don't get all the data by default. You only get a random subset. And in fact, what you get is only a random subset of 3 features. So at the very top of the tree, the root node, 3 features are selected at random. And let's say these are the features that were selected. So for tree 0, the very first part of the tree, the very top of the tree, the root node, all it gets is this FNL-WGT feature, relationship, and hours per week. And then the tree then has to pick, that's all it gets. Now, it's entirely possible that all 3 of these features stink, that they're terrible, but that's okay. Because as I said before, a random forest, we have lots and lots of trees. So inevitably, some of the trees are going to stink, and some of the trees are going to be awesome, and most of them are going to be somewhere in between. Just like in the real world, if I get a big enough crowd, some of the people are going to be highly educated, some of the people are not, some of the people are going to be really smart, some are not, some are going to be liberal, some are going to be conservative, some are going to be male, some female, in between, right? All these kinds of different things. So it really simulates this idea of the wisdom of the crowd and diversity. Okay, so we're okay with this. We don't worry about it because we're going to have lots of trees. So this random shake of the features, not a big deal. So if we continue with this example, we can see here that the tree has to pick from these features and picks the best one for the root node. And then typically trees are built using 2-way splits. And what ends up happening is the left side of the tree here, right? So this is the root node. The left side of the tree gets another random shake, gets another 3 features at random. And let's say this time it's age, education, and marital status. So the tree then has to pick the best of these 3 features for the side of the tree. Once again, maybe the features are good, maybe they stink. We don't really worry about it too much. Same thing over here. over and over and over again. Now notice this. Notice that relationship is repeated over here. That's totally okay. Depending on what's going on with the feature, the algorithm keeps track of what features are available for random shake. So if more information is available in the feature, it can be chosen again over here. If a feature's information is all used up, for example, let's say it's a yes-no indicator, so all the yeses go down this way and all the no's go down this way, the information of that yes-no indicator is all used up. If you want to think about it that way, that yes-no indicator will never be picked at random again. The algorithm keeps track of all that. You don't need to worry about it. So it's super, super awesome. So that's how this works. All right. So conceptually, you now know how the random forest works. It's basically a collection of decision trees, and it uses bagging and feature randomization to make sure all the trees inside the forest are as radically different from each other as possible. So let's start talking about the data set that we're going to be using in this particular crash course, which you will get, of course, if you opt to have me send you the files. Okay, so we're going to be using what's known as the adult train data frame here, the CSV file. I'm loading it up in pandas, and you can see all the different features here, just like what we saw previously. And if I keep scrolling to the right, you can see all the other features. Okay, so notice that some of these features over here are duplicated because I've just, in the notebook, I've just scrolled to the right. And let's say we're going to build a random forest from this. And we want to evaluate the quality of the random forest in terms of its predictions vis-a-vis the OOB data. Now I'm going to expand upon this. This is awesome. This is part of the reason why we love random forests so much. At least I do anyway. Okay, so this is our data set, which you will get if you opt to have me send you the files. And then what we can do is we can say, okay, look, of these features, I'm only going to use a subset for this particular crash course. And the reason for that is pretty simple. One, I want to make sure that the code fits on my slides. And two, I want to provide you with an opportunity to play around with the code. You'll get the Jupyter Notebook if you opt for it, and you can play around with it. You can try different features, and you can just tweak my code and see what happens. It's a very, very useful learning exercise. We're going to create a new female. Excuse me. We're not going to create a new female. Yeah, this is not Weird Science, the movie. We're going to create a new feature called female, which is simply just a binary indicator. Because in the original data set, there is a feature called sex, a column called sex that has a string male and female. And if we one-hot encode these, which I talk about extensively in the decision tree crash course up here, we don't want to one-hot encode this. It's actually redundant. So what we're doing is we're saying, look, instead of using male and female, we're just going to have a binary indicator, ones or zeros, right? Anytime the US citizen has been designated as female in the original data set, we're going to have a 1, otherwise we're going to have a 0. So that's the feature we're going to use. And then I'm going to use all of these features. I'm going to use 1, 2, 3, 4, 5, 6, 7, 8, 9 out of 14 features for this random forest model. And once again, that's so that you can get the code and play around with it if you'd like. So I'm going to use these 9 features. And of these 9 features, these are categorical features: race, occupation, and marital status. So these need to be one-hot encoded. Once again, check out this video up here for more details. And you can see here I'm going to use pandas to do the one-hot encoding. Now, this is not the only way to do one-hot encoding. There's an even better way using a scikit-learn class called the one-hot encoder. But right now, I'm just keeping things simple, and I'm using the getDummies function from pandas, which will one-hot encode everything. And you can see here in the code, I'm accessing my adult trained data set, but I'm only accessing the 9 features here from the all features list. I'm also prefixing my names, and then I'm only one-hot encoding these particular features. And then I'm calling info on it. And what I'm going to show you now is some of the results. Okay, and what you can see here is these features will remain unchanged because they're numeric features, so they don't need one-hot encoded. Female here, 1s and 0s, no big deal. And then over here, we can see marital status divorced, marital status married, armed forces spouse, married civilian spouse, married spouse absent, so on and so forth, right? And there's a whole bunch of other columns here because you can see there's actually 32 columns total after the one-hot encoding, but this just gives you some flavor of what's going on. The version of pandas that I'm running on, that I used to make the code, encodes these as Booleans, trues and falses instead of 1s and 0s. But behind the scenes, Python treats trues and falses as 1s and 0s anyway, so no big deal. So I got all my features prepared. Now, if I go back up a slide real quick, notice that my data frame that I'm going to be using to train my random forest is called adult_x. This is a naming convention. So it's my subset of features that have been one-hot encoded and prepared. So they're good to go to be used with the random forest classifier algorithm from scikit-learn. Now, my labels are actually string values, less than equal 50K, greater than 50K. Scikit-learn can't work with those out of the box So I'm going to use something known as the label encoder, this class right here. And the label encoder will actually take those string values for the labels and then transform them into numeric representations akin to one-hot encoding. So I create a label encoder. I then ask the label encoder object to fit and transform my labels. Now, if you're not familiar with scikit-learn, this is a naming convention. Fit means go learn from the data, go learn what you need to know. And transform means take whatever you learn and then apply it to something. So in this case, go learn what labels I have as string values in this particular column of this particular data frame, and then transform it into the appropriate numeric values, which I'm storing as adult_y. Once again, this is a naming convention that's common in scikit-learn. You can call this anything you want, but obey the naming convention if you can. And then I can ask my label encoder object for the original classes, and you can see here the string values. Less than or equal to 50K, greater than 50K. And then I can print adult_y, and you can see the numeric mappings. So everywhere in my data frame where the value of label was originally less than or equal to 50K, adult_y has a value of 0. Reflexively, greater than 50K, I've got a 1. A couple things you need to know at a high level about label encoders. 1, they actually set up this mapping based on alphanumeric ordering. So if you sort these strings, this string comes before this string. So that's why it's in the 0 position, and that's why this one's in the 1 position. So keep that in the back of your mind. It's not based on business semantic, it's based on alphanumeric ordering. 2, this scales. In this particular example, I've only got 2 labels, less than or equal to 50K, greater than 50K. However, if I had 3 labels, 4 labels, 5 labels, doesn't matter, right? I get 0, 1, 2, 0, 1, 2, 3, 0, 1, 2, 3, 4, so on and so forth. So this all works to your data set, no problem. Now I've got my training data prepared. I've got my labels prepared. Now I'm ready to actually train a mighty random forest. So here's the code for that. So I import the random forest classifier, and then I instantiate a random forest classifier. In scikit-learn, when you instantiate one of these classes, one of these algorithms, the parameters that you provided essentially define the training regimen, the way the model will learn, essentially, including the hyperparameter values. So let me walk you through this code and explain what's going on here. So n estimators is the number of trees. So by default, this class has a value of 100 for n estimators, meaning by default, it will create 100 trees. I'm using 200 here to show you how to change it. Empirical evidence has shown that a good value for this is actually 500. 500 trees, which is why I said earlier, we don't really worry so much about the randomization because we're creating so many trees, it all works out in the end. So we're going to say, okay, let's go ahead and get 200 trees in the forest. And I just picked that number arbitrarily, by the way. Don't read too much into that. Next step is this parameter here called OOB score. And what I'm going to do here is I'm going to say, hey, look, random forest, I know that for every tree you create a bag, and every bag has out-of-bag data. So what I would like you to do is use that OOB data to score the trees. Now, let me explain what I mean by that. So imagine we're building tree 0 from bag 0. Bag 0 doesn't have all the rows of data, so there's some OOB. So once I've learned the tree, once the tree's been trained off of bag 0, I can then take OOB 0 and say, hey, tree, make predictions on the OOB. And then I can see how well the tree's predictions match the actual labels from the OOB data, which is awesome. Because then what that allows you to do is say, all right, how accurate is that tree? And then I can do this 200 times. How good is this forest, generally speaking, in predicting OOB data, predicting data it's never seen before? And that is so useful. I'm going to go into more detail on this on a future slide. Okay, so that's what this does. Next step, you can actually train random forests in parallel, right? Because if I have bag 0 and bag 1, these trees can be trained completely independently. So if you have multiple cores, multiple CPUs, you can set the njobs parameter. And it's 1 by default. And I've set it to 2 here just to show you what can happen. You can set this to any number you want, but make sure you don't set it too high. Otherwise, your machine might slow down tremendously. Okay, cool. And the last thing that we want to talk about in this particular crash course is random state. The random state parameter essentially says, look, if I want people to see the same thing that I'm seeing, I got to set a common starting point. If you set the random state to 1, 2, 3, 4, 5, which is a totally arbitrary number, and you run this code over and over and over again, you'll get the same exact results every single time because the randomness, if you will, always starts from the same starting point. Because computers actually can't really do truly random things, by the way, just so you know. They look random to humans, but technically it's not. This is a great example. Start here at 1, 2, 3, 4, 5, and then every single time you run this code cell in your Jupyter notebook, you'll get the same exact result. So in the real world, you don't usually need to set this unless you need reproducibility. You need to be able to replicate the same thing over and over again. But since I'm teaching a class, I certainly need that, which is why I'm setting it. And then I store this as a object I'm calling adult_rf for random forest. And then I ask it to fit itself to the data, to go learn specifically, hey, use these features to try and learn how to accurately predict these labels. And that runs for a while, chunks away, blah, 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 blah. And then what I can do is I can actually say, okay, cool. Since I've asked the random forest to keep track of the OOB scores on a tree by tree basis, I can actually ask it for the overriding score. So I'm just going to print it out here. And what you can see here is I'm asking for the OOB score. And this just means give me 4 decimal places. And then you can see down here, hey, the estimated accuracy with the OOB data is 81.35%. And this is actually super useful because what you do is you then say, look, in general, if I was actually going to use the random forest in a production scenario, and I put it like, maybe I hook it up to my website or something like that, how accurate do I think the predictions would be going forward once I hooked it up to my website? And the OOB data provides you an estimate with that. And it says, around 81.35%. And maybe that meets your business requirements. Maybe it doesn't. If it doesn't, you're going to want to go back and add more features, ensure new features, get more data, get new data, whatever it might be to push that up. Now, just for grinsies, what I'm doing here is I'm also demonstrating how you can use a trained random forest to score itself against some arbitrary data set. So this is a bit funky, so follow along with me here. So I'm going to use my adult random forest, and I'm going to ask it to score itself against the original training data set. Because notice I'm passing in my features for my training data set, and I'm passing in my labels for my training data set here in 4 decimal places. And you can see here that I get over 96% accuracy, which is kind of what you would expect, right? If this random forest algorithm is super powerful and you train the random forest from the entire training data set, you would hope that it's pretty accurate against the entire training data set. And that's exactly what we see here. We've got the accuracy, the OOB accuracy, the OOB score for the random forest all up. And that's super useful. But what's even more useful is diving into the actual OOB predictions themselves to actually understand more about patterns of what's going on in terms of the predictions. And that's a bit abstract. All makes sense here in a second. But first, what I need to do is I need to extract out the OOB predictions from the random forest object. And this is some code to do that. It's not the only way to do it, but you've got the code. You can copy and paste and reuse it in your own projects if you would like. So first up, I'm going to create a new data frame, a data frame of my OOB predictions. And what I'm going to do is I'm actually going to grab the OOB decision function. Interesting name. So it's an attribute on my random forest object, and it essentially has the predictions. And then I'm going to label the columns based on my label encoder classes. And then I'm going to store that in a new object I'm calling OOB_preds. So the easiest way to understand what this code is doing is to actually look at the output over here. Ignore this and ignore this. So notice that my columns are my labels, less or equal to 50K, greater than 50K. And what you can see here is the OOB decision function data. Now, this is cut off, obviously, so there's actually a lot more rows here than I'm displaying. But what this is saying is, hey, out of the 200 trees in the forest, how many voted for less than or equal to 50K versus how many of those 200 trees voted for greater than 50K? So for example, row 0, 100%, 200 out of 200 trees voted for less than or equal to 50K, and 0 voted for greater than 50K. Down here, row 6, you can see that 37.6-ish% of the trees voted for less than or equal to 50K, and 62.35% of the trees voted for greater than 50K. So that's how this line of code can be interpreted in this, as this table right here, this data frame right here. Now what I'm going to do to this data frame is I'm going to add a label column, boop, and I'm just going to populate it with zeros all the way down. Then what I'm going to do is I'm going to change the value of the label column based on the voting for greater than 50K. So what I'm going to say here is any place where more than half of the trees in the forest voted for greater than 50K, make the label value equal to 1. So the easiest way to think about that is to look at this particular row right here. Notice that more than 50% of the trees voted for greater than 50K, so the label is now 1. Now here's what's really super cool about this code. This greater than 50% is convention. Majority rules voting. That's the way the random forest works by default. But using this code, you don't have to do that. You can change this to be any value you would like. Maybe you think that's too easy. It's too easy to get a label of 1 at 50%. So maybe you set it to 60% or 70%, that sort of thing. Totally up to you. Based on your business need, you can do that. And then what you can see here is print OOB's shape. And what this tells you is that there's 15,016 rows of data, because my original data frame had 15,016 rows of data, and I get back 15,016 predictions. So everything lines up great with my original training data frame. Same number of rows, same order. Everything's great. This table by itself, not super interesting. When it gets super interesting is when we use this table that we just created, this data frame that we just created, to visualize the predictions using something known as a confusion matrix. And here's the code for creating a confusion matrix. And I'm not going to drain this code because, quite frankly, it's much easier to understand it based on what it produces. This is what I see. I see a confusion matrix, this visualization here. So first up, ignore this color band here. This is just trying to tell you in color how many rows of data exist, which is not super useful, to be quite frank. What you really want to pay attention to is along the x-axis here is the predicted label. So this is the label predicted by the forest. Less than or equal to 50K, greater than 50K. And then along the y-axis here, we actually have the true labels. The label in the data was actually greater than 50K, and the value here was actually less than or equal to 50K. Now, what that means is the correct predictions are along this diagonal here. The model predicted less than or equal to 50K. The actual label was less than or equal to 50K. The model predicted greater than 50K. The actual label was greater than 50K. And this is awesome. The score that we saw earlier is just everything all up. But now what we can do is actually evaluate how well our model's doing vis-a-vis the labels. And what we can see here is that in general, our model is pretty good for both types of labels. The accuracy for the less than or equal 50K labels is good, around 81%. The accuracy for greater than 50K, about the same. This isn't always the case, by the way. You'll often create confusion matrices for your machine learning models, and you can do this with any machine learning model, by the way, not just random forests. But let's say you're using random forest. You can do this with your random forests, and you might find that it's really, really good at predicting one label and terrible at predicting another label. And that's really, really super powerful for you to know, because then you're like, I need to find more data or use different features that might help me boost up my prediction accuracy in places where I'm not very good or my model's not very good. So this is awesome. Very, very good kind of thing. All right. So there you go. Like I said, very much a crash course. If you'd like to continue your learning, these are some great books. Okay. So first up, this is a free book. There'll be a link down below the video in the description. Free PDF, you can get this. This is a high-level survey text. It covers a lot of different kinds of machine learning techniques. Nothing in particularly deep levels of detail, but you can certainly get it. It's useful for free. Okay, so links in the description below. If you're interested in learning the random forest like really in depth, you have to start with trees, because random forests are based on trees. And this is the definitive book on decision trees right here. This is super mathematical. It is not an easy read whatsoever. There'll be a link down below in the description as well. So just keep that in the back of your mind. This is not for the faint of heart. Now this textbook right here, which is on my dining room table, you can see, is awesome. This is the first edition. This book is not Python specific, and it covers many algorithms, but it's at a much deeper level than this book does. And this book is great. So it covers decision trees and random forests, boosted decision trees, cluster analysis, market basket analysis, all kinds of stuff. So this is like my absolute favorite textbook on machine learning or data mining. You can think of those things as being synonymous. And there'll be a link in the description below as well. So to the second edition, this is a great book if you're looking for something a little bit more in depth. It's not Python specific, but it also talks about the algorithms. It's got some math in it, but it's not super, super mathy. This book is extremely mathy, but this one's a much, much more approachable read for lots of other people. By the way, just in case you tend to prefer a self-paced online course instead of books, no problem. Check out a link below below the video here in the description, and I'll give you a link to my machine learning online course and a coupon code to save 20% off if that's the way you roll. There you have it. Thank you very much for watching the video. I hope you found it useful. Hope it got you excited about the power of the random forest. It's a great algorithm. And my next video will be talking about the bias variance trade-off, which is one of the single most important concepts in all of machine learning. So when that video is available, it'll show up as a tile here. And in the meantime, I'll put up another one of my videos for you in case you want to watch it. And you can stay tuned for that video when it comes out. And that should probably be in about a week or so at the time of this recording. So until next time, please stay healthy, and I wish you very happy data sleuthing.